In this video, I'm going to talk more about normal force. So it's an elaboration of what we have done before. It's incredibly important that you understand reaction or the normal force from an atomic level, because that is going to help you understand the other forces or interactions that we look at. And so there are three standards that are associated with this video. So one of them is I can identify the types of interactions between objects. And so one of them is this normal force or reaction force. Another one is I can explain the mechanism of the normal force. We've talked about that before, and we're going to talk about it more. And then the last one is I can explain the mechanism of the friction force. So normal force is related to the friction force, and we're going to see how in our next video or next set of assignments. But in this assignment, we're going to look more carefully at the normal force. So observations that we've made already is that the harder the hand pushed on the spring, the harder the spring pushed back on the hand. And we could see that as we pushed down harder on the spring, we saw it compress more. And so that more compression meant more push back to go to the original size of the spring. And we could feel that, hurting our hand or feeling the pressure against our hand. The harder we pushed it down, the harder the spring pushed back. We also saw that the harder the hand pushes on the foam, the more the foam compresses. And again, that compression is what gives that push back or push up on the book. And then I tried to connect this to a compression that you couldn't see, but it's something that you can feel. So the harder the hand pushes on the table, the more the hand feels the table. And that feeling the table is actually the table pushing back on you. So how does that push happen? We can't see a spring, but we can feel differences in the pressure that we feel coming from the table when we push down on it. And so our explanation for this was in the video by V. Sauce-Michael, You Can't Touch Anything. And so he showed a couple of diagrams, which I've repeated here. And so it stems from this idea that all matter, and so us, the spring, the table, we are all comprised of atoms. And atoms have electrons on their outer surface, and electrons are all negatively charged, and they all repel each other. So when our hand comes near to other atoms, the negatives are touching the negatives and they repel each other. And the closer that I try to get to the electrons, the more they push back. And so that's why the harder I push, the more pressure I feel, because the electrons are pushing away from each other or repelling each other more. And so this ends up with some interesting things, that we actually are hovering on everything, or we really never touch anything. So like even when scissors cut through paper, the scissors aren't actually touching the paper. They are just breaking the bonds between atoms. They're moving the electron clouds apart from each other. Okay, so this is our springy atomic model. And this is the idea that individual molecules or atoms have electron clouds. And the electron clouds can change size and shape. The reason why they're called clouds is because they have kind of a fuzzy edge. They don't have like a really finite edge. And so this fuzzy edge allows us to kind of manipulate where the edge actually is, or the size of them. And so as we try to make the electron clouds smaller, so we make them smaller, they repel each other, and that's the push that we feel, or the pressure that we feel, or the touch that we feel. So our example is we have the tabletop is made of atoms or molecules, and in between the atoms or molecules, we have bonds, and these bonds are actually the overlap of electron clouds. So when we put something on the table, like a bowling ball, we move, again, we can't see this with our eyes, but we move the electrons closer to each other. So the electrons on the edge of the bowling ball are repelling the electrons on the top of the table. And so I don't show it with my bowling ball, but the electrons basically squish up to try to get away from each other. They can never touch each other. And so as the electrons and clouds of the table, or the molecules on the table, get closer to each other, they repel. And so these red lines show the direction of the repelling, and they all add up to be the reaction force or the normal force. So when we have the table surface with nothing touch it, we have this uniform distance in the electron clouds of every single molecule or atom. But then when we have something that touches the table top, the electrons of the object touching the table top repel the electrons of the table, and they make the atoms go closer together. So they're like trying to get away from the object that's touching them. It can only go so far, and so they push back because these atoms can never be pushed into the next atom. The atoms all have to have space between them, or a space for the electrons to go between them. So this reaction force, or the normal force, is the push of electron as we try to make the electron clouds move closer, or we push against the electrons. They're pushing back. Okay, they're repelling back because negative charges, they repel. So that push is the normal force. Okay, let's look at some applications. So every object made of matter has an electron cloud. Anytime two objects touch each other, and I have touch in quotes because we know nothing ever touches, it just hovers near, their electron clouds repel each other, and that is what adds up to the reaction or normal force. And this is repelling, so it's a push. And it just so happens that it's perpendicular. But the reaction force can point in any direction. Oops, thought I had one more bullet there, because it just depends on how the objects are oriented to each other. So if I have table and then I push my hand down, the push is up, okay? But what if I have a wall and I'm pushing sideways, okay? Pushing sideways on the wall, what happens is I compress, or the electrons on my hand repel the electrons on the wall, so they move them closer to each other. And then again, the wall repels back or pushes back, and that is the reaction force or normal force that I feel on my hand. Okay, so now the normal force is going to the right. Okay, so we know it can go up, it can go to the right. We can just like flip this whole thing. It can go to the left. What about if I hold an object against the ceiling? Okay, what do you think? Well, if I push an object against the ceiling, guess what happens? The normal force actually points down because the electrons on the ceiling repel the electrons on the book. And so the ceiling has a normal force on the book that points down. So can the size of the reaction or normal force change for an object? And the answer is absolutely. Okay, we can imagine that I'm holding a 100-pound weight that's I'm barely holding it on the surface of a table. And so weight is the force due to gravity. So when I'm barely holding it back, the table's not pushing back very much, okay? But when I let go of the weight and the full 100 pounds is on the table, I'm able to squish a lot more atoms or get them to be a lot closer to each other. And so the pushback from the electrons is a whole lot more. When electrons go closer together, the push is a whole lot more. So again, I can think about the normal forces changing, and I can actually feel that on my hands. So I can do a little bit of a touch. I've got a little bit of a normal force. I do a stronger touch. I've got a stronger normal force. And then I do a really big touch, isometrics, and I've got a really big normal force. So the normal force can change depending on the conditions. Okay, So labeling forces. I'm going to go through this in detail. I kind of alluded to it on the last video. So there are 3, sometimes 4 parts, but there's a minimum of 3 parts. So the first one is you must have an F. It's not optional. Okay. The second one is that you have the initial of the feeler, and this is the object that is the focus of the free body diagram. So if I say do a free body diagram for the table, this letter is going to be T. Okay. If I say do a free body diagram for a ball in flight, then this letter is B. Okay, so this is what I'm doing the free body diagram for. So here's a pro tip. All the force labels for a free body diagram should have the same first initial, because the free body diagram represents all of the forces acting on a single object. So if I'm doing a free body diagram for the table, the first letter on every single force label is going to be T for table. Okay. All right, that's part 2. So part 1, F, part 2, initial of the feeler or the object that I'm doing the free body diagram for. The second or third part is the initial of the dealer. So what is the object acting on the object that is the focus of my free body diagram? So if I'm doing a free body diagram for a table that is sitting on the floor, then this initial would be F for floor. First initial T for table, second initial F for floor. So this is the object that is attached on the system schema to the feeler. So you just look on your system schema. So reaction or normal force happens anytime 2 solid objects touch each other. So anytime they're touching, normal force. It's caused by electron clouds of atoms being compressed. They don't want to be compressed because they repel each other. They want to be as far away as possible. And so it's always a push. It's always a repel or push. It can point in any direction. The direction depends on the orientation of the touching objects. And then between any 2 objects, the reaction force can vary if a third object pushes or pulls on one of them. So this is me holding up the weight. I can hold it up and make the reaction force on the table or on the weight by the table. Let me say that again. If I hold a weight, the normal force on the weight by the table is less than if I let go of the weight and the weight is resting on the table. Force labels have 3, sometimes 4 parts. And when we get to the 4th part, I'll let you know.